Hi, my name is Manish Gupta, and in this video, I'm going to talk about DEXA, which is basically deep encoders with auxiliary parameters for extreme classification. So let's get started. Okay. So on this slide, I'll try to explain how typically extreme classification is done in recent algorithms. Okay. So it is typically done in two stages, and therefore here I'll explain the two-stage extreme classification training approach, and then a particular problem with this approach, which has motivated folks to come up with DEXA. Okay, so a little notation first. So extreme classification is the problem of learning a multi-label classifier where the number of labels could be extreme, basically in millions, right? So let's say that there are n data points and L different labels. Number of labels is in millions. The data points are going to be represented as xi, yi, I going from 1 to n. Right? Now, typically in extreme classification, you would have an encoder to be able to encode these data points and sometimes label text as well from the space of a vocabulary space or a TF-IDF space to a D-dimensional space. Right? And also you want to ensure that these D-dimensional representations learned using the encoder are normalized. And therefore, you can think about these encoded representations as points on a unit sphere of D-1 dimensions. Okay, so that's that. Now, typically, extreme classification algorithms work in two stages. The first stage learns the encoder. The second stage learns the classifier. So classifiers are nothing but SQL vector representations per label. So WL is that classifier vector for label L, right? Now, ideally, one would want to just do joint training of both the encoder and the classifier together. So the encoder theta and the classifier W's, people would want to sort of learn them together by trying to minimize, this loss, which essentially says that the similarity between a label M and data point xi should be higher than the similarity between non-relevant label L and xi, at least by a margin gamma, right? So if I have two labels, a relevant label L and a non-relevant label, M, then what I want to do is to ensure that the similarity between the data point and the relevant label, in this case, the relevant label is L, right? So the similarity between the data point and the relevant label is higher than the similarity between the data point and the non-relevant label, at least by a factor of gamma, right? So of course you want to minimize this thing. Okay. Now, and one would want to do that for all data points n and for all labels. Of course, there are few positive labels, but for all negative labels also. Now, when the data points are in millions, let's say 1 million, and the labels are also in million, let's say 1 million, this joint training is basically very, very difficult, right? It's like a million squared kind of things to be evaluated, terms to be evaluated, and you would not want to do that. Okay. So joint training is therefore difficult. So therefore, what people typically do is to do hard negative mining. And they basically say that I'm not going to consider all negative labels associated with every data point, but I'm going to only look at a short list of a few selected hard negatives, right? Of course, I'll take the positive label L, but then I'm also going to take some negatives because I have to basically do this ranking kind of a loss function. And so therefore, I'm going to take a few hard negatives. And there have been techniques for mining hard negatives, which I've covered in several videos in several of the previous videos. Okay. Now, keeping this hard negative mining in mind, people have proposed, and by the way, hard negative mining was awesome, and people could just do with that. However, the problem is that still learning the encoder and the classifier, both of them together, is difficult on a single GPU, especially for large data sets. Therefore, people have proposed modular training where there are two modules. So specifically, Endgame actually came up with this two module technique where the first module is going to learn the encoder parameters and the second module is basically going to learn the classifier parameters. Okay. So the idea is that in the first module, you assume that your classifier is super simple. So it's basically you can use the encoded representation of the labeled text ZL. ZL is labeled text. So encoded representation of the labeled text itself as a classifier for the label L, WL, right? And if you do that and you substitute that sort of there, what you obtain is that you essentially are trying to minimize this gap. So essentially, WL has just been replaced by the encoded representation of those labels. Okay. Now that's the first step, and the first step essentially leads to learning this theta nicely, the encoder representations nicely. And then you use that encoder representation so as to initialize your classifiers WL as um, this encoded representation of the label text plus some variables. So they call them as free parameters to be learned in module 2. Okay. So these free parameters sort of try to capture the association between the label and the data point from the training data. Okay. So in the module 2, that is what you're trying to optimize for. So you basically want to learn your eta Ls, and you learn them by actually using the same formulation, by saying that, hey, I'm going to rather than using or rather for WL, I'm basically just going to use this same formula, and then I'm going to minimize. Assume. Oh, by the way, in module 2, you keep your thetas constant. So you basically freeze your thetas and don't update them in module 2. Okay. So that's the typical endgame based training. And in endgame, of course, people use in-batch sampling. So that's what people do so as to essentially have negatives obtained from the same batch itself for efficiency purpose. Now, this all is good. The story is good, but then M1 itself leads to a distorted encoder. Now, the point is that this assumption that we made about being able to represent the classifier, approximate the classifier as the encoder representation of the label text is an assumption. And this basically leads to a distorted encoder representation learning, which leads to suboptimal performance overall, even after you fine tune even after you fine tune this representation in module 2. Right. So the idea is that there is a semantic gap between WL and the encoder representation for the label text. Right? How do you match that gap, or how do you basically care for that gap is what DEXA studies. So how is the DEXA model trained? Let's discuss how is DEXA model trained and how does it make up for that semantic gap. Right? So again, a little summary here first. So traditionally XE models have been two-stage, as I just talked about, but then even before that, people had proposed one-stage models where people would just do Siamese kind of training, where you basically have your data points and label text. Essentially, you try to encode them using some encoder, and then essentially you come up with the relevant data points for relevant labels for a data point by just looking at this similarity score between the embedding for the data point and the label. Okay. In the two-stage methods, basically, as I mentioned in the previous slide, in the first stage, you essentially learn these thetas where you want your data point and the label embedding to be as close to each other as possible for relevant ones and far away from each other for non-relevant ones, right? But in the second stage, what you do is to also learn these eta Ls, thereby learning WL, such that you essentially learn a WL representation, which is closer to relevant data points and far away from non-relevant data points, right? So people have also come up with fusion methods where you could take the score from your classifier and the score from your encoder so as to come up with a better ranking score. Okay. Now, and as I mentioned, the bigger problem has been that this WL is not very close to your encoder representation for the label. Okay, so therefore DEXA does something smart. DEXA basically says that let's have label correction terms during encoder training also. So rather than dealing the label correction, rather than dealing this eta L kind of stuff into the classifier step, let's basically bring it to the encoder step itself. Okay. And the idea is that they do it in a smart manner. They basically say that these correction terms that have to be added, related labels must have very similar correction terms. So the idea is that if you basically have a correction term also in the encoder itself, then your encoder and classifier training becomes very similar, and it becomes very complicated because overall number of parameters are too many. There are eta Ls for every label, remember, and then there is this large encoder also. So therefore, they want a shortcut. So they do not want too many. So this size matrix, eta L is very large, right? So if you think about eta L, if your dimensionality is D and labels are, L, then LD is the size of this eta matrix. Okay. However, what they want to bring in are correction terms such that they are shared across similar labels, related labels. Okay. So that finally I end up with a very small matrix. Maybe I have a C cross D matrix, where or maybe I can probably call it as like K cross D matrix, where and let's call this matrix as the auxiliary variables matrix. Okay, A. Okay. So such that related labels actually share these correction terms. So basically saying, I'm going to basically call this WL minus E theta ZL as a correction term A. And the idea is that if L and M, if labels L and M are very similar, then they must share the correction term AK. Okay. So now how do you find which labels are related? Well, to find which labels are related, they basically just do hierarchical balanced k-means clustering. So you basically just have all the labels, and then you essentially start off with an embedding defined by PIFA. So basically, aggregated across your essentially aggregated across your um, uh, you know, across your data points, right? Text related to data points, or it could also be a representation learned using the labeled text, right? So you essentially do k-means clustering, hierarchical balanced k-means clustering on top of that. And then using they use Distilbert-based encoder, and then this leads to capital K clusters, which is much smaller than capital L. That is why this matrix eta is very tall, but then this matrix A is very small because it just contains a unique auxiliary variable vector AK for one cluster rather than for each label. Okay. So now how does this work? How does DEXA work? So the way DEXA works is that in module 1 itself, essentially what you're doing is rather than approximating WL as E theta ZL, you're essentially saying that, hey, my WL is going to be E theta ZL plus these auxiliary variables. Okay. And these auxiliary variables are one per cluster. Remember, one per cluster rather than actually having one per label, they're one per cluster. Okay. And of course, when you add these things, you randomly initialize this and you learn it over iterations, of course, as part of encoder iterations itself. You also normalize this. So this is standard normalization. Essentially, this is the standard normalization. You need to take the vector and divide by the magnitude of the vector to get a unit vector, right? That's that. So it's not a big deal. You essentially take a d-dimensional representation and divide by the norm so as to basically have a vector on the unit sphere of dimensions d-1. Okay. So if this math is too much, you can ignore this math, but just think of it as like a vector which is obtained by normalizing rather than just using E theta ZL, you're actually using E theta ZL plus A for that particular the cluster for the label L. So C of L basically just maps the label L to the right cluster, and you basically use the auxiliary vector for that label. For that cluster. Okay. And then this is basically copy paste from the previous slide. This is not a new formulation. You want to minimize and compute your theta, right? And your A's. So you basically want to learn your theta and your auxiliary variables such that this entire thing is minimized, right? So essentially rather than WL, I'm basically just replacing WL there or WM and WL there, essentially to just ensure that those labels which are relevant for a data point are closer to the data point compared to those labels which are non-relevant, as simple as that, and with a margin gamma, right? So nothing changes there. So in M2, you basically freeze your encoder, you throw away your, so you freeze your encoder, basically you freeze your thetas, okay? You take your normalized representations for every label and assign it to a temporary representation called ZL. In fact, you assign it to WL. Okay. After you assign these vectors, remember these are like actual numbers. You assign these vectors of numeric, of floating points, right, to W. After you do that, you throw away A's. Your auxiliary variables are no longer useful. They were just there so as to essentially get a good initialization for your WL for the second stage for the classifier WL. Okay. Once you've done that, you basically go ahead with your usual business, right? So essentially you throw away your A's. So of course, the auxiliary variables are just auxiliary. They're not a part of the overall training, final training. Okay. So you throw away those. And essentially in module 2, you go ahead with the same kind of training as you did in typical endgame style. So nothing differs, right? So basically, whether it is label L or label M, you essentially just go ahead with the same typical module 2. It's just that the initialization in module 2 has changed from WL being initialized to E theta ZL plus eta L to E theta ZL plus the auxiliary variable. Okay, auxiliary variable. And once you do that, of course, there is no eta L now. Essentially, the idea is that or rather there is an eta. Yeah, there'll be etas, of course. And then what you want to do is to essentially, of course, learn W's in module 2 while trying to care for this ranking loss. Okay. So that's that. So the only way that DEXA differs is that at the encoder part, there is a usage of auxiliary variables so as to take care of the semantic gap between WL and E theta ZL, right? Between the classifier representation for the label L and the encoder representation. Okay. So how does DEXA perform? So the inference pipeline for DEXA is super simple. You after you've trained your WLs, you actually encode them in a index, in a fast lookup index, and you can basically so that you can do MIP search on top of it, maximum inner product search. Okay. So when a data point xt comes in, you basically get its embedding using your distilbert encoder, which has been trained, theta has been trained in M1 itself, right? You query the MIPS so as to get the closest labels, and closest labels in the sense closest with respect to this inner product. And then you also combine your classifier scores with the label similarity scores. You fuse them, right? And that basically is you rank labels by those scores, and that's your final output. Okay. Now, while you were doing this clustering business here, so as to essentially have auxiliary variable per cluster, what would happen is that the head labels could actually sway the clustering a lot, right? And therefore, what they also do is to do head label partitioning. They basically say that, hey, let's take some head labels and then assign those head labels one cluster per head label. Okay. And then the remaining labels, yes, you cluster them amongst, let's say if you used H head labels and you wanted to have K clusters, so K minus H clusters, you basically cluster the remaining torso or tail labels into K minus H clusters. Okay. So that's that. Now, how does it perform? So well, as you can see, I've basically shown the results for one data set here. So on precision and propensity score precision, basically they have compared across several baseline methods. Some of these are essentially DPR, BM25, Colbert, etc. are all dense retrieval methods. Remember, extreme classification and retrieval are actually pretty similar to each other, right? So these are dense retrieval methods, and then these ones are, of course, all up to decaf are essentially so these ones are extreme classification methods. NC2 Rocket QA are all dense retrieval methods, and you see DEXA is fairly better compared to most of these methods. Many of these baselines are pretty new. So NGame was also 2023 method, and so on. Okay. So as you can see, it is like 6% and 15% more accurate than embeddings using these state-of-the-art extreme classification methods. So in the paper, they also show some results on the proprietary datasets, but for that, you'll have to look up into the paper. Interesting, they also observed that yes, there will be some overheads on training time, but that's minimal. So because of course you're bringing in these auxiliary variables in the encoder training, so there is some overhead, but not too much. Also, model size does not increase too much. In fact, auxiliary variables are not even a part of the model, so there is absolutely no overhead on the model size at all. Okay. So now this chart is interesting. It shows you how many auxiliary variables are good to have, right? So as you see, if there are no auxiliary variables, this is practically endgame, right? This is actually endgame itself because there are no auxiliary variables. So then you do the usual business of M1 and M2, encoder training in M1 and classifier training in M2 without any auxiliary variables, right? That's endgame, right? And if you use 120,000 auxiliary variables, or vector or clusters, right? So essentially, you get a significant boost in precision at one. Okay. So what is interesting to observe is that as you increase the number of auxiliary vectors that you have, your precision increases, basically saying that auxiliary vectors are doing the job that they are supposed to be doing. Even with a very few auxiliary vectors, you observe that you are already getting quite some boost. But yes, I mean, investing slightly more actually gives you more boost as well. Right? Now, just increase the RAM that you require for training the encoder, but the model size does not change because you throw away auxiliary vectors after your initialization for the classifier or the module 2 is done. Right? Okay, so in summary, two-stage training actually makes extreme classification feasible, but leads to poor encoder training because of the semantic gap between the classifier representation for the label and the encoder representation. DEXA essentially uses auxiliary variables to train robust encoders, trying to make a match between M1 and M2 modules. DEXA involves minimal overheads on training time and absolutely no overhead on the model size, but leads to leads to an extreme classifier which is better than many dense retrieval and extreme classification methods. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn and look at my research on my homepage. Thank you.